In this lesson, we'll start our discussion on big idea number 2. So how does the type of bond between two atoms determine the physical and chemical properties of a compound? And focus on learning target number 5. By the end of this lesson, you should be able to determine the type of bond between elements and draw proper Lewis dot diagrams of compounds. Depending on what type of compound you're drawing, there's a different notation. You recognize ionic compounds because they're made up of metals and nonmetals. These atoms transfer electrons to create stable ions. Because the ions are oppositely charged, they attract each other in what's known as an ionic bond. Whenever we draw ionic compounds, we use arrows to show where the electrons are transferring to, and we write full charges on each of the ions. Often it takes more than two elements to become stable. So continue to add enough atoms until everything has 8 electrons or no electrons in their outer shells. Here's an example: lithium and oxygen. Lithium is in group 1 on the periodic table. That tells me that it has 1 valence electron. Oxygen is in group 16, so it has 6 dots on its Lewis dot diagram. Because lithium is a metal and oxygen is a non-metal, they're going to form an ionic bond. Lithium wants to get rid of its 1 valence electron to become stable. So I'll draw an arrow saying that that electron has gone over here and give lithium a 1+ charge. Now you notice that the oxygen only has 7 electrons. It's not stable yet. So what I'll do is I'll draw another lithium atom over here to donate it another electron, and then my oxygen will be stable with a 2- charge. Pause the video and try some out on your own. Here are the answers. It took 2 fluorines to take the electrons from magnesium. Fluorine's going to have a 1-, magnesium would have a 2+ charge. Potassium and chlorine become stable in a 1-to-1 ratio, each with a 1 charge. It took 2 aluminums and 3 oxygens to make a stable aluminum oxide compound. Molecular compounds are 2 or more nonmetals that share electrons to become stable. This is known as creating covalent bonds. Depending on how equally the electrons are shared, different types of covalent bonds are made. This can be predicted by looking at the difference in the electronegativity values between the 2 atoms. The periodic table in the back of your textbook has the actual electronegativity values for all the elements. What you would do is you would look up the 2 elements that you want to bond together, subtract the 2 numbers, and use the following scale to figure out what kind of bond gets formed. If there's an electronegativity difference between 0 and 0.5, then it means that there's relatively equal sharing of electrons between the 2 atoms, and the atoms have no charges on them. This is known as a non-polar covalent bond. If the electronegativity difference is 0.5 to 1.7, it means that one of the elements is significantly stronger than the other, and there's unequal sharing of electrons between the 2. This creates partial charges on the atoms. A partial charge means that it's a fraction of a charge. It's not a full 1+ or a full 1-. Instead of putting a 3/4 - or a 0.25+, we use a little squiggle to show that. It's actually the lowercase letter delta in the Greek alphabet. If you have unequal sharing of electrons, this is known as a polar covalent bond. Any electronegativity difference over 1.7 is considered an ionic bond. There's one element that is so much stronger than the other that it totally removes the electron from its partner, creating full charges. Using the periodic table in the back of your textbook, figure out what type of bond would be formed between these elements. Here are the answers. The bond between sulfur and oxygen has unequal sharing of electrons. It's a polar bond. Sodium and iodine are a metal and a nonmetal. If you do the math, you get an electronegativity difference that gives you an ionic bond. Because bromine and bromine are the same element, they have a difference of 0. That means they're completely equally shared, so it's a nonpolar covalent bond. And C and H have a difference of 0.4. That's also falling into the nonpolar bond range. Remember, diagrams for molecular compounds use a different notation than ionic ones. Ionic bonds, we use arrows showing where the electrons are going, and full charges. When you're doing a diagram for a molecular compound, make sure that you use the clock method when you're placing electrons around the atoms so that you get the molecule's correct shape. This will become important in the next lesson. We use circles to show electron pairs that are being shared. These can also be represented by sticks, known as a stick diagram, to save time and for a neater look. Any polar bonds in the compound need to have partial or slight charges. Here are some examples. Here I'm going to draw 2 hydrogen atoms. Hydrogen is stable with 2 electrons because it only needs to fill the first shell. I'm going to draw a circle showing the 2 hydrogen atoms sharing those electrons. Electrons that are shared in a bond are known as bonding pairs, if you come across that terminology later. Now, because both of these are hydrogens, the electronegativity difference will be 0, and each of the atoms will have no charges. My diagram is now finished. An alternate way of drawing this is by using a stick diagram. I draw my atoms, and I put in a stick for every bonding pair. PBr3 is an example of a molecular compound with polar covalent bonds in it. I start by drawing my phosphorus. It's in group 15, so it's going to have 5 dots. And I'm going to use the clock method to place those. Start at 12 o'clock and go around before I start to pair. 3 bromines can share the electrons with the phosphorus to become stable. I represent the bonds being made by drawing circles around the shared electrons. Now these are polar covalent bonds. There's an electronegativity difference between phosphorus and bromine of 0.7. That means the bromine will actually pull on this pair of electrons stronger than the phosphorus. This gives the bromine a slightly negative charge. Now this happens in each of the bonds. Because phosphorus is losing the electrons some of the time, it will have a partial positive charge on it. Now my diagram is complete. I've used circles to show electrons being shared, And because I have a significant electronegativity difference, I've put partial charges on each of my atoms. The stick diagram for PBr3 is a little bit more simplified. Make sure, though, that you don't forget to still put on the partial charges. Try the next three molecules on your own. Here are the answers for the last three compounds. Notice that nitrogen is sharing three bonding pairs. This is known as a triple bond. Also, nitrogen has pairs of electrons that aren't involved in a bond. These are known as lone pairs. In the stick diagram, I've drawn them so that the lone pairs are opposite the bonds. This is because lone pairs take up more room. So you always draw them as far apart as from other negative electron groups as you can. This affects the overall shape of the molecule. For example, when you're drawing water, water is a bent-shaped molecule. The hydrogens are not straight across from each other. If you use the clock method when you place your electrons around the oxygen, starting at 12, 3, 6, 9, and then starting to pair, you'll get this correct diagram. Because lone pairs take up more room, they're always going to be beside each other. The main issue here is we're trying to draw a 3D molecule using a 2D diagram. If you ask in class to see a model kit, we'll be able to show you the shape of water and why it's drawn bent instead of straight across. Remember, the last step for drawing a molecular compound is to figure out what type of bonds you have using electronegativity and applying partial charges if needed. You need charges on the water molecule and the NHO molecule. Notice that the nitrogen here, we don't have a partial charge on it. It's a little hard to figure out. It's pulling harder on the hydrogen electrons, but it's losing out to the oxygen. To be honest, it doesn't really matter what the partial charge is on the nitrogen. We could figure it out by doing some calculations, but it's not going to matter in our next lesson, so we're going to leave it with no charge. Try out the homework for this lesson listed on the schedule.